Hi, my name is Galen Tunnicliffe, and today I'll be reviewing Lab 1 on charge tapes. So for an intro, we use Scotch tape to determine the charge on each piece of tape to observe the transfer of electrons, and we assume that the tapes are acting like point charges. We use Newton's second law and Coulomb's law for this, for the force of gravity and the force of an electric field. So we assume that we treat the tape as a point charge, and we also assume that the charge is evenly distributed along the length of the tape. We ignored air resistance and assumed low humidity to simplify. Some interactions that we observed is that when we put the tape on the table and we put a hand or a book there, it attracted slightly, which were both neutral objects, the hand and the book. But when we put tape 1 and tape 2 next to each other, they repulsed each other. And we put a negatively charged pen next to it, there was a strong attraction, indicating that both tape strips are positively charged. So you may ask, what if the positive charge on protons and negative charge on electrons were switched? Nothing really would observationally happen because opposite charges would still attract and like charges would still repel. And it's also important to handle the charge tapes as little as possible because if we handle it too much, it equalizes and neutralizes the tape. So these are some measurements that we'll be using later on. We use these measurements to find the value of Q, which is our charge for each tape, which turns out to be about 2e negative 8 coulombs. So using that calculated Q, we can figure out the number of electrons that would be on our tape, which is roughly 1.3 E12 electrons. And then using the area of the tape, which is determined by the length and the width in the previous slide, we find that the number of atoms on one side of tape is roughly 4.6 E17 atoms. So we take the ratio of that and we get 2.788 E negative 6 electrons to one atom, indicating that there's much more protons, indicating a positive charge. So we can also take a look at our glow script model. And as you can see, we have the constants on the left, which is our coulombs, and our scale, because we have to scale up the arrows, and our d, which is our initial separation distance, which is the equilibrium distance. The two red spheres that you see are the positive charges of the tapes, and both have a mass of 0.00024 kilograms. And then to calculate the weight or the force due to gravity, we just multiply that by 9.8. And the gravity arrows are in green. One is covered up on the bottom by the force due to the electric field, but it's the same magnitude and direction. We get our R by subtracting the position of position of 2 minus position of 1. Then we get our charge by taking the square root of the weight times the radius squared over k, which is derived from equating the gravity and the electric field forces. We define a new function called E-field to find the electric field of a particle of two particles, and then we use that to create an arrow showing the force to that electric field on one of the particles. So we input this twice, and we switch the charges in each to create two orange vectors that you see, which is up and down on each point charge. This is the end of the presentation, and thank you for your time.